All right, hello. My name is Isaac Merritt. As Eric just introduced me, I just graduated with my master's at Berkeley, and this is my thesis project. This was my kind of brainchild for about a year, and the idea was to take data 8S content and move it into Snap so that younger students would be able to interact with the material a little more easily. So DASIS, as far as I know, is the first comprehensive data science library to be implemented in Snap. Snap is a block-based beginner style language for new students, especially in the educational sector. And it's a little bit more accessible than Python, in my opinion. As a Snap graduate myself, I took CS10 here at UC Berkeley. I can speak very much to the efficiency and the beneficence of Snap overall. Students will be able to learn data science principles without having to go through the weeks and sometimes months required to learn a brand new typed language. The block-based environment has shown to be a much smoother and a much quicker introduction to programming. Data science is interdisciplinary, as I'm sure everybody here knows. So any and all high school age students will have the ability to use these principles going forward in their own careers, whichever way they choose to use it. This is intended to be a jumping off point for a class like Data 8 in the future and taking their data science educations further at university. So at this URL, I have all of my published content. This is sort of a mini course with 4 modules that students can work through and that teachers can help students walk through. It is intended to be a bit more of a handhold than Data 8 is. There's a little bit more infrastructure, a little bit more showing what's going on, and then allowing the students to take what they've just learned and do something themselves. It's all accessible online. It's all through CS10's website. And that's where I put all of the content. Yes.
Get a grade for it?
A grade.
Yes. Or like a sticker.
If you would like to go down to your local craft store, then yes. But it's not a student feedback machine. It's more similar to how CS10 labs are at Berkeley. So it doesn't have auto graders yet, and it doesn't have automatic feedback, but absolutely, if you'd like to do that in person, you may. So a little bit about myself. I just graduated with my master's under Professor Josh Hugg. It was a fantastic experience. I graduated my undergraduate in computer science with a minor in data science a year ago, which is still wild to believe that that was only a year ago. I've TA'd in computer science and data science classes here at Berkeley. I taught CS10, the class that introduced me to computing overall. And then I also taught Data 6, a class that I believe you'll hear a little bit more about today. I'm the sole developer of the DASIS library, but there is a plan to continue the project with undergraduate researchers in the near future. I have 1 or 2 interested students who will be taking over the project and sort of expanding on it as much as they can. So currently the library includes support for data visualization and the table infrastructure overall. The data importation process is, I'll talk about it in a moment. You can use any size CSV as long as the CSV you're using is clean. That is the one thing. Cleaning data in Snap is a little bit sketchy, but overall, as long as your CSV is clean, it's going to work. We have bar plots, histograms, line plots, and scatter plots. Those will all show up on the Snap stage for those of you who are familiar with Snap. It is the area of the UI just intended for image use. And so we take advantage of that and do all of our visualization over there. There are also table methods and table manipulation. Those are going to be your SQL style, data science, Data 8 style queries. Those are all their own individual blocks that students can either nest or implement in order. So as I mentioned, you can load any CSV into Snap. It is currently, the whole library is not currently available on Snap's base platform, but it is available at the website that I did provide. So you can access DASIS and you can access all of the modules that I've created via that link. When importing data, we have a CSV that'll bring it into Snap. There's a block that students will use to convert that into a table object that DASIS can use and that they can use to do anything that they'd like. And then the table methods and visualizations that I talked about, those are the meat and bones of what the library does. So we load the data set in using the import feature of Snap. When creating a variable, you can right click, you'll allow that import option, brings the data right in, and you'll be able to create the table right there in Snap. No additional work required. The table object has 4 attributes. You're going to have your data, the number of rows, the number of columns, and the number of the names of the labels that exist in the table. There's a block that'll help you visualize all that so that students can jump right over that. And you also have these convenient accessor methods so that students do not need to interact directly with the unabstracted object. And then querying the table is, as I said, very similar to SQL or Data 8. Any query that they use, they do not need to know how it works underneath. There's no low-level programming knowledge required. There's no need to understand what's going on behind the scenes. They just click the button and all the magic happens for them. So they do not need to fully understand what's happening under the surface. This is intended to be introductory material. So this is just some of the, I know on here, they kind of look kind of dark, but they're supposed to be orange. These are some of the querying blocks. This is a sample of some of the more prominent blocks. You have your groups, pivots, ordering. There's a whole slew of functionality that I don't have to list out each one. But the idea is that students can run these as many times as they want, and they will not change the table. They'll always have the original data. They can always save it for later. These blocks do not edit the table. They create a modified copy. And for example, with group and pivot, that can be sometimes a difficult conversation to start to have in an educational setting. They do not need to understand what's going on underneath. They just click the button, and as long as the inputs are correct, it's going to work. As I mentioned, that view table block is going to make sure that they do not need to interact with that table object. They'll jump right over the abstraction barrier and they can use it as they please. They never need to know that it's stored as four items. They can use the accessors and use that view table block, and it works out very well for them. These are the blocks that do affect the table, which can be a little bit difficult when learning on new tables. So students will need to be informed that the data will be edited when they use these command blocks. They have a different shape, and they at times do even indicate within the block name that they're permanent. These will make changes, and students should be well aware that if they click that, it's very hard to undo those changes to a table. So they do need to be used with caution in general. This is really the part that I enjoyed creating the most, which would be the data visualizations, which are supposed to be purple despite their blue appearance up here. These 4 blocks do all of the work for them. They do not need to modify a table and get it into the format that it can be visualized. They simply provide the table they want, the columns they want, whatever other arguments they require for that block. It does all the work under the surface automatically. They do not need to have created a table that would work with a data visualization. They just click the button and it goes. So some examples that we have here in Snap, these are bar graph. We have a bar graph, a histogram, a line plot, and a scatter plot. These are the base, the sort of the default uses of the data visualization blocks that we have in DASIS. But if we look at the next slide, they also get more advanced. We can group, we can see different colors. They automatically do all of this. The block does all of this for them. They do not need to worry about it. They do not need to pick the colors or anything like that. It's intended to have abstracted as much of that detail away so that students will feel more comfortable making a mistake or accidentally doing something wrong once. It's totally fine. They'll just fix what they need to do. And yeah, I have to say personally, this was just so fun to do in Snap. Having worked with Snap as an educator and as a student, this is just, it was so much fun. So yeah, DASIS is intended to be a bridge for students to get to data science content earlier. Even if that doesn't mean teaching them data 8 right up front, they don't need to have any statistics. The class generally stops at statistics and probability conversations. Those are to be left for another class. It is really just to get them interacting with as much content as possible. And yeah, I feel as though if I had been handed this opportunity in high school, I would have jumped at it. I would have been ecstatic, and I would have found data science much earlier than I did. So that was my aim in creating this project. And for the future, I would love to see students who are even younger being introduced to these things at a more basic level. It doesn't have to be that by the end of it, they can type in Python and they can create these big projects, but just planting those seeds early. You don't start a student in math by teaching calculus, start with addition and you work your way up from there. So yeah, does anybody have any questions? All right.
Yeah. Thanks, Isaac. Yeah, unfortunately, Isaac is going on to other things.
Yeah.
And this is an awesome project that has a whole way to connect to the BJC world and a whole way to connect to high school curriculum, but it needs somebody awesome to take it on. So if anybody has any ideas of who would be interested or who to engage with, you know, or where we should go with it, it's like looking for some high school help.
Is this like a Python library or?
It's like a Snap library. So Snap is its own sort of like world that there's a ton, like if you'd ever know, like what's called Hour of Code. Like my kids were learning in Snap in, I don't know, elementary school. So it's like a common first programming thing. So he's built a library that sort of mimics the Python library we think of as data science, but does it in Snap.
Then is there a way that you can access it?
Yeah, the URL I mentioned earlier in the slide, you can also go to cs10.org/VJC-R, and you can scroll to the bottom and the modules are there as well.
So it's publicly contributed into like a public space.
Yes, you do not need an account, you do not need any of that.
You can just go click and start using it.
Absolutely.
Okay. On to Chris Piles and Otter Grader.
All right, hello everyone. I'm Chris Piles. I graduated from Berkeley a year ago. And while I was here, I spent a lot of time working at the division, building auto grading infrastructure that we now use in several of our courses. And I'm sure we talked about Otter yesterday when we talked about Data 8, Data 100. So today I'm just going to do a quick introduction to Otter, what the idea behind it is, and kind of like how you would use this from an instructor perspective. So to start off with a little bit about kind of auto grading in general, basically the idea of an auto grader is you have a way of automatically assessing a student's assignment without requiring somebody to go in and read it and assign a grade manually. For courses like Data and Data 100, where you have 1,000, 1,600 students, this is really something that you need in order to be able to offer classes at that scale. And so generally the way auto graders work is that they take a piece of student code, run it again in some kind of safe environment, and then run unit tests against the code that the environment produced by the student's code. And this is true of most auto graders, and it is true of Otter as well. So Otter came out of an effort a few years ago to take the grader used by CS61A, Data 8, and Data 100 at the time, called OKPy, and make it something that people could use without needing to like spin up a server to grade themselves, right? So OKPy relies on a backend server that actually grades students' notebooks, so they don't use something like Gradescope. Well, OKPy doesn't use Gradescope. And we wanted something where you could have it and run it locally, where you could like spin up a server if you wanted to, and kind of do it however. So AutoGrader came out of that effort. It started initially as completely local, where an instructor would download assignment files, create Docker containers on their machine, and grade assignments in those containers, and then kind of generate like a CSV of grades that you could do with whatever you could do whatever you wanted with later. Early on in the process, we realized that Gradescope had this great auto grading platform, and so we kind of adapted the process to work with that as well. And so now, 3 years later, we have Otter version 3 is what we're on right now. And since then, we've added support for R. So Otter was originally designed for use with Jupyter notebooks, but we also work with Python scripts. You can also use R Jupyter notebooks and R Markdown files. And we have a tool included with it called Otter Assign, which is used for generating, which you can use for like designing your assignments, where you write out questions and solutions and tests in an easy to write Jupyter notebook format. And then, like I said, you can use Otter locally to grade or with a third-party service like Gradescope. So really, like the core abstraction of Otter is if you provide compute, a place to run Otter, Otter will take care of the rest for you and manage the grades and executing assignments and wrangling your tests and everything else. So Otter was designed with three core populations in mind. So we designed for students by providing a client library that students can use to run public tests that are distributed with the notebook or the assignment as kind of like a check to say, you know, is my work on, am I on the right track? Is my answer reasonable, et cetera. Then for graders and TAs who are going to be, you know, assigning grades for assignments, you can also write hidden tests that are only known by the auto grader that students will never see, that prevent students from using the auto grader as like an oracle and, you know, just spamming the auto grader with submissions until they get a perfect score, while still allowing you to accurately assess a student's performance on an assignment. And finally, with professors in mind, in that we can grade classes really at any scale that you want, and be compatible with several different learning management systems. So at UC Berkeley, we've got quite a few courses that are using Otter, and I picked three to highlight right here. So of course, we have Data 8 and Data 100, which are introductory and core upper division data science courses, both very large classes. I think Data 8 last semester was 1,600 students and Data 100 was 1,000, with, you know, large staffs. And I think this is not even the whole staff, this is just the kind of UGSIs, doesn't include the tutors and the AIs. And then also we have another course at Berkeley called Public Health 142, which is a statistics fundamentals class for biology and public health students. That class is run in R, and I believe they're using R Markdown with Otter for their assignments. And so that's a medium-sized class of 350 students with only about 8 TAs. So like clearly Otter is a very scalable solution, right? And that was kind of what we had in mind as we were designing it. So the original kind of scalable workflow that we came up with for Otter was for Data 100. Over the summer of 2020, I think, we had our first offering of Data 100 that, or was it 2020 or 2021? 2020. Summer 2020, the summer instructors for Data 100 took the opportunity to convert all of their assignments to Otter from OKPy, and this is the workflow that we have used since we did that. So basically, you start off by developing an assignment in this master notebook format that we call Otter Assign, or that is used by Otter Assign. Then you take that notebook, run it through Otter Assign as a tool, and it'll generate a configuration zip file that you can upload to Gradescope to create your grading Docker image. Then you'll use MD Git Puller to distribute the notebook to students. And that distribution, that Git repo that MD Git Puller is using also contains the public test for your assignment. Students run through the notebook, put in their answers, and then at the end of the notebook, there's a cell that will generate a zip file for them, and they take that zip file and upload it to Gradescope. And that has their submission and any other artifacts, like there's a log of the checks that they ran. That's also included in this. Then you have Gradescope spawns a Docker container, runs the submission and assigns grades. And then, so what we do for Data 100 is because the assignments can have written questions as well. We have two assignments that are set up on Gradescope. One is an auto-graded assignment where a student uploads their zip file to. The other one is like a PDF assignment. So what Otter does is it takes the notebook the student submitted, parses out only the answers to their written questions, and uploads that to the written assignment on Gradescope. So that way the TAs or the tutors can just go through and like click and see just the answer the student wrote to the question, none of the filler text, none of the code, and make it really easy to just, you know, go through, boom, 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 answer and assign a grade for each question. And so, you know, Otter was kind of hoping, like, the goal of this is to alleviate the stress of manually grading and take advantage of Gradescope's templating system to make it really easy to grade those written questions. And finally, once you've graded all of the written questions, you publish the grades for both assignments on Gradescope and use that platform to handle regrades. So besides that, besides Gradescope, there's also a local workflow where you use Docker containers on your machine to do this. And it's a very similar workflow. And really the only difference is you're collecting those zip files in whatever LMS you would like. And then at the instructor, once this due date has passed, you download all of the zip files in batch, and then use a command provided by Otter to create a Docker image for grading those on your machine. Then you create a container for each submission, grade it, and then Otter will put together a CSV of all the grades for you that you can then use to, write grades on your LMS or do whatever else you need to do, and wrangle the grades however you need to. And so with this, manually grading and regrades and students' ability to view grades are all just handled on whatever LMS it is that you're using for your course. So I've mentioned auto assign a few times already. So auto assign is one of the biggest features included in auto assign from the grading, of course. And it is a tool that we use for taking in a notebook that contains all of your questions, the solutions, and the tests for each question, and creating two distribution versions for students, and then a version for instructors that have the solutions in them. So this is a fork of a tool called JAssign that was created for OKPy that was being used by Data 8 and Data 100 before Otter came around. And it kind of abstracts away a lot of the greediness of tools like Otter Generate, which is the tool that makes that zip file that you used up to create your Gradescope image, and the OK test format, which is the format that we use for writing AutoGrader tests. So the input to auto assign is a notebook that looks kind of like this, where you have a question and you can see that it's delimited by these raw notebook cells that have some configurations in them. So you say, okay, here's the beginning of a question, and then you have the narrative of your question. Then you say begin solution, and then you put the solution code there with some comments that are used to do solution removal. And then you say, okay, here are my tests, and then you have some cells with your tests in them. And then you say, okay, that's the end of the test and the end of the question. And so you can write both coding questions, which is the example given here, but if you also have written questions you want to include, you can do that. And then you just add like a metadata thing in the begin question cell that says, manual is true. And so that'll tell Otter that this is a question that's not auto-graded, but is manually graded. So we also have a format for our Markdown files. The format for our notebooks is pretty much the same as this. There's a couple intricacies around the test cells, but it's largely the same as the notebook. But this is the format for our Markdown. It looks very different, and it is actually because with version 3, we released a new format for the notebook. So previously, the notebook looked a lot more like this, our Markdown file, but now it's very different. And so ready to be distributed to students. So writing tests. So as I mentioned, tests are written in the OK format, which is a format that relies on Python doc tests. So you can see here in this test file, this is the test file generated by AutoAssign. You can see it's formatted the same way as the Python interpreter is. So this is, again, a legacy from OKPy. And this is the format that you would write tests in. Honestly, there's no real reason for you to write tests manually, because we have auto assign, which makes everything very easy. But if you're going to be writing, for example, an assignment that uses like Python scripts instead of notebooks, you would have to write tests like this. But you can make them formatted a little bit nicer. So there are two kinds of tests, as I mentioned. There are public tests, which are visible to students. And generally, we use these to allow students to check whether their answers are like formatted correctly or otherwise reasonable. So for example, checking that a variable has the correct data type or is in a range of values. And then there are hidden tests, which we generally use to determine the exact correctness of an answer. So like, x equals 2 or something like that. And these tests, very importantly, are only known to and run by the auto grader. So students should never get these. These should never be included in any public repo students have access to. Otherwise, you kind of like lose the security of the hidden tests. So when a student runs their answer, so this example is pulled from the auto grader notebook, but this is what it looks like when a student runs the grader in the notebook. So you can see if they've got it right, it just says you passed the question. But if they fail a test, there's some output here where it says, okay, I was trying, assert this, that, the correlation of this is supposed to be this value, but I got an error when I expected nothing to come out. So I failed this test, and this is kind of the output that students get, and they can use to debug their assignment as they work through it. So that's kind of a view of what Otter is like right now. So currently we're working on version 4 of Otter, which our goal is to have a stable release out by the start of fall. Some highlights for version 4 are a new test file format. So as I said, we have this kind of little hideous format created from OKPy. What we'd like to do is be able to write tests that look more like PyTest, where you can just write functions that assert some condition. And if you throw in an error, that's a failing test, but if no errors are thrown, that's a passing test. So that's the new format we're going to have. And then, like I said, we're also going to have a new Markdown format for our Markdown format for our assign that's going to be more similar to the notebook format that we use right now. So default auto assign format v1. So there's two versions of the auto assign format for notebooks. There's the old version and the new version that was introduced in version 3. In version 3, the new format is opt-in only, meaning that you have to specify a flag when you run auto assign to say, hey, I'm using the new format of notebook. When we move to version 4, the new format will actually be the default, and you'll have to use a flag to say, I'm using the old version format. And then in version 5, we'll completely remove the old format. Then we're also going to be adding support for using Otter's notebook client on Jupyter Lite, which I think Yuvi is going to be talking about here in a couple minutes. Then beyond version 4, we have some things that we're looking at, like PDF errors. So there's some intricacies around like using LaTeX to export PDFs of notebooks, and we want to make that experience of when that goes wrong a little bit better. We also want to add more features to Otter. Sounds the same, but it's different. There's no E. This Otter OTTR is Otter's R client. So this is what you would use in an R notebook or an R Markdown file to run the checks, similar to the grader.check cell of the Python notebook. And then we're also looking to refactor our Docker images, make them a little easier and a little smaller. So this is what that new test file format looks like that I was talking about that looks like PyTest. You can see there are just functions, you write assert statements, but the main difference is that you decorate them with this test case modifier decorator that provides some metadata about, for example, the point value of the test, whether it's hidden, etc.
That looks nice.
But yeah, this is what we're hopefully going to. Not quite clear how this is going to work out with the auto assigned notebook format, but still, this is kind of the new format we'll be looking at. I think we're going to remain with the default being OK format if you're using auto assign. But TBD, I don't exactly know how that's going to go out, and I really should know because it's going to come out soon, but I don't. And then, here's the new R Markdown format. It's a little small, I apologize, but as you can see, the main difference here is that where in the Python notebook format, we had raw notebook cells with these like hashtag begin test. We're now just using HTML comments here in the same way we were using those raw notebook cells. So this is the new format for our Markdown that'll be available in version 4. And it's kind of just bringing our Markdown back in line with the format for notebooks. All right, finally, if you look at the presentation, I have some links here. you notice there was like one notebook that I used throughout this presentation as an example. There's a link to that notebook there if you want to look at it and run and play with it if you want to. It's actually a, I don't know if Eric has talked about Data 88, but it's an old project from Data 88 that we don't use anymore. So it's included there. I have a link to the documentation for Otter and another information link here with information about how you write doc tests, because there's some subtleties there about string comparison. Also link to the GitHub repo, and then if you have a feature request, find a bug, etc., please open an issue on the GitHub repo linked here. Or if you have a general question, feel free to reach out in the Slack, which there's a link to join the Slack right there, and or ask on GitHub. And I don't want to cut too much into UV's time, but if there are a couple questions, I can take them right now. Yes.
Is there any facility for plagiarism checker?
Not currently. It's something we would like to add. So there's some logging that goes on when a student runs checks in the notebook, and there's a log file that's included in that zip file they generate. But there really isn't. The issue that we have around plagiarism is that there's no real way in the way that Otter is designed to like compare submissions, because it's kind of run on demand and separately in separate containers. So it's something we're actively looking into, but there isn't anything yet. Yes.
Do you have an R notebook version in that example?
There is not in here. If you look in, I don't know if it's present in the whole screen. Okay. So there's example on everything on the documentation under creating assignments and Otter assigned format v1. We'll reload. So this page is the documentation for the format for the notebook format, and it's the same for Python and R. If there are any differences, it's noted here. I don't have, oh, you know what, actually? GitHub.com, PDS, infra, Otter sample. Okay, I don't remember the last time I updated this. Looks like it was 10 months ago. So this might be in the new format, but I don't know. This is a repo that I created as like when we first developed Otter for R. This was like an example repo. I will have
You
to
should get one from Brookman.
Yes. I will add a link to this. Sorry.
And the one you're gonna put in that super notebook R or Markdown?
This has both. This has everything R. Okay, that has everything for R. I'll try and update it later if I haven't already 10 months ago. Any other questions? Yes.
Just quickly, is the functionality that said that you can split the assignment into two grade scope assignments, is that available now? And
Yes.
or what is it called in the documentation so I can find it?
It's not like, it is available now. It's not like specifically like a feature or something. You just set, like basically what you'll want to do is when you write your assignment config, so this block,
We're gonna have to move these.
yes, sorry, I will just answer this really quickly. There's a thing here called template PDF. You set this to true, that'll generate a template that is like spaced out for all of the written question answers. And then you upload that, you just create a separate grade scope assignment, you upload that as a template. And then there's a couple configurations. Sorry, let me just find this here. Under generate, you have a token, you have to generate a token for grade scope. And so what it does is it, when the autograder runs, it generates a PDF and then there's a post request to Gradescope's API to upload that to that other assignment. So you'll need to put the course feeding assignment ID in here, but that's how you configure it. And I'm sorry I can't take any more questions because we've got to turn it over to UV. Thank you all very much.
Thanks for your time. So great. All right, you got your tabs lined up here? There's a couple. All right. Uh-oh, Colonel died.
Everything is dead.
This is the famous UV Panda who is one of the core contributors to the Jupyter project, and one of the builders of Jupyter Hub, and somebody who's been keeping everything going behind the scenes the whole time.
I paid him to say that. Thank you, Eric. Yeah, so I'm one of the upstream contributors to Jupyter Hub. Been involved with the Jupyter and Jupyter ecosystem for a few years, and I currently help run our production data hub with the data hub team, which is Eric, Balaji, Jonathan Felder, and Ryan Levitt. So now we're going to go through and I'm going to give you a couple of demos of things that are like sort of kind of here in a few months together that are like, I think, like going to help bring this to more people and provide like functionality that will make people's lives easier and enable use cases that are currently kind of difficult or not possible. So we're going to split this between me and Balaji. So this is going to be mostly a sequence of demos. So the first one is there's a new project that's been going on called Jupyter Lite. So I will just out of breath. So like if you've gone through the data classes and stuff yesterday, one of the core infrastructure we run is Jupyter Hub, right? Which is like something in the cloud where people click a link and then you have a notebook, and then you can just, students can just get tracking without having to install anything on the local computer. But from an instructor's infrastructure perspective, this either means that, you have someone who understands enough about like clouds and sysadmin to run this, or you're like paying someone to do this. And this, of course, can get problematic. So the Jupyter Lite project helps to bring Python with the whole data science ecosystem into the browser directly. So this means you can run notebooks, you can use all your regular Python libraries, like all of the Data 8 textbook code and everything, and soon order without the student having to install anything or the instructor having to maintain anything. So this doesn't work for like super complex, you're doing like planetary scale analysis, it's not going to work, but for something like Data 8, it's going to work pretty well. So this is the demo. This is the Data 8 textbook. I made a small fork of that. And, if you go through, you can see some of these have executable code in them, right? And then if you go to the launch icon, it gives you a couple of options. And a new option in this demo, it says Retro Lite. So this will just open up. So the thing is here, there's no infrastructure going on for this. This is just running in the browser. It's just static files. Nobody's being like, there's no like monthly bill that comes at the end of the month to run this, right? But it's exactly the same code as is running in the classroom, as is running in the Jupyter Hub itself. So I execute it, and
There's no install.
Yeah, there's no install. The student has to do nothing. It's the same workflow as if you were running on Jupyter Hub. You click a link and it shows up. It takes a minute to load, but so people are working on making this faster. Like you can see here, we have to install the data science package when we first use it. People are working on making sure it's bundled in. But like after this, it just it's just regular Python. Like whatever you're doing, this just works. Like if I don't tell you that this is not running on infrastructure on some cloud that someone's paying for, it's very difficult to tell that's actually what's happening. So this is like fairly new. I think it's been going on for maybe a few months. It's maturing. There are still problems, because of course it's like you're taking something that's been running on like Linux and Unix and Windows for a long time and trying to run it completely within the browser safely. There's no access to the student system. You can't use this to steal stuff. So there's still like work in progress, but I think this is going to be pretty good for like a lot of use cases where you can just, like modern computers are pretty fast, right? Like, and for most cases, like Data 8 type things, you don't need like 400 gigs of RAM. So a student's laptop is more than good enough, as long as we don't start by having them spend 3 days trying to get things installed and working. So I think this is like a great amount of progress. And if anyone wants to try it out in their class, you can do that. Like, again, there's some rough edges still, but as you can see, it mostly works. You can test out the link. Like this works for all, like this is the entire Data textbook deployed. You can like try it out. You can go through the various notebooks and then see how that looks like. So that's
You got it to open directly in Retro and not in Lab.
Yeah. I got it to open directly in Retro, not in Lab. So you can see all of the chapters and everything, and you can like go through and look at it. And this is just all of the changes are just saved in the user's browser, like it's not anywhere else. So all right, so that's Retro Lab. The other useful thing that comes from here is you can like this is even more of a work in progress, but I just wanted to share. So this is like a notebook, right? Like in a document format, and then there's some code here. So you can also live execute this. This currently uses, Binder. So there is some cloud server somewhere that's going to spin up and then let us execute it. And that means two things. One, it's going to take some time, right? Because the public MyBinder is provided as a free service, or, you need to pay for a cloud resource. Now people are working on integrating Jupyter into this. So, you can just click run and it just works. So this took a bit, but, like we can integrate this in such a way that no backend resources are needed at all. So you as an instructor can build material that is like much more immersive. You're not having to bring people out into like a separate environment to do things, right? Like, so I
It's
think,
really changing what a textbook is.
yeah, right. Like it becomes just so much more interactive. And you can do that now, right? Like, because clearly this works, but the bar for what it takes to have this running well, I think is just coming down, and this can be easier for people to make and cheaper, because I think, I don't think anyone wants to go through like getting university IT to approve like, $100 or $80 or even $1 per month, right? There's a lot of overhead, and getting rid of that completely, I think is very, very good. Am I doing on time?
This is all sitting on top of the GitHub repo, right?
Sorry?
Is it sitting on top of the GitHub repos that are supporting the?
Yeah.
Git 8?
The question was, is it sitting on top of the GitHub repo that's supporting Git 8? Yes, it's built out of the textbook repo. I have a fork that just has this config that will get merged in. So you can actually see this from the main textbook itself, hopefully in a couple of weeks. But yeah, it just uses the same infrastructure. That's right. Yes.
What are some of the advantages of using something like Jupyter over like Binder?
So the question is, what is the advantage of using something like Jupyter or Binder? Like Binder costs like $7,000 a month to run for people, right? Like, I mean, it's a public service for everyone. So, but like if you have Jupyter, that cost kind of goes away. And there's also like definitely a bit of a speed advantage. Like you're like waiting for the server to start and like go do its thing and make it happen. But they're just different kinds of things.
You're also not supposed to teach like 100-person class on Binder.
Yeah, I mean,
That's not really the spirit of Binder. The spirit of Binder is like, I could just open something if I want to see it.
yeah,
But once you get to like teaching a lot of students, that's not really the.
yeah. You're ideally supposed to run your own infrastructure. Because if you have 100 students, they're all on Binder and it breaks for 2 of them, what are you going to do? You either leave those 2 behind, or you just have to like kind of stop your class, right? That becomes a problem the larger scale classes you go on. But yeah, they're just like different tool sets. Like there are a lot of things you can do in Binder that you cannot do in Jupyter. It's just a much more lightweight version that, like has like the primary thing is nobody has to pay for Jupyter. Somebody is paying for Binder right now. That's not you. Right. So that's like really the primary difference. Okay. So next set of demos. Okay. Another thing that's in a very good demoable state, and I think people have been using it in production a little bit, is something that people have been asking for a long time, which is real-time collaboration. So let me see, which is Google Docs style collaboration, where like I'm typing something, I give a link to someone, they can see exactly what I'm typing. Like if you are in person somewhere and you have a student, they're running into problems, you can just go like look at their screen, right? While if you're not, that becomes more difficult. You can do Zoom, but it's not quite the same as sharing a keyboard and a mouse. So real-time collaboration on Jupyter has been something that people have been asking for a long time. It's been worked on for a few years. It's reasonably stable now. We're still working out some kinks on just making sure that there's no data loss and things like that. But for a quick demo, this is lab 1 of data 8. And so if I'm a student, I'm like, just working through it, blah, blah, blah. And I'm like, oh, this fails. I mean, I can see what to do with it. But in this hypothetical magical story context, I don't know. So I can ask for help, right? Like there are GSIs, there are TAs. So I can right click this lab and say copy shareable link. Then that will give me a link very much like Google Docs that I can share with someone. And then they will have access to my notebook in a way that they can interact with. So Balaji is here. I've already shared the link with him. So I can, so you can see now there's like a cursor and that's him typing. So, you can do things and then he can also execute like code, like whatever. And then I will see it happen practically like, immediately. So you can see that that worked, right? And of course, we can both edit different cells at the same time. We can execute different things at the same time. So it works. I mean, if you use Google Docs, you know how this works, right? It's just bringing that to here, along with the ability to actually execute the things that you're working on. So this works on Jupyter Lab. This works on RetroLab. It's working pretty solid now. Jupyter Lab 4.0 should come out in a few months and be even more solid. Fernando, who's going to give a talk after this, has been trying this out in his class. So he's always on the cutting edge, and this works pretty well. So I think this is going to be great for collaborations. Right now, you have to basically like copy and give this link to a user to get them to use it. But there's also work going on into getting into group functionality, so you can be like, all right, you're doing a project, 5 of you. This folder you all have rights to, and you can collaboratively edit it anytime you want, sort of like Google Drive. So, sorry, all of that's coming through and should be pretty good. So I think by the time, the next year this workshop goes around, I suspect that Jupyter Lite would be in a fairly solid state that people can generally use it for their things. So like, a lot of your infrastructure cost situation just kind of disappears.
Yeah.
And Jupyter Lite also works with real-time collaboration. So you can have that going without, needing specific infrastructure as well. So, all right, that's my demos. Very quick set of questions, and then I'll hand it off to Balaji. Woo! Yes. I would say Jupyter Lab 4.0 is going to come out in maybe 2 to 3 months. I think it's good to use in the fall for advanced classes. We'll turn it on again for Stat 159, which is Fernando's class when fall comes. And if we make it through the end of fall without anyone losing anything, then I would be comfortable saying it's ready for production. So our students lose things, so yours don't have to. Yes.
Is there a server involved with the collaboration? Like, how does it deal with firewall?
Yeah, I can. There is a server doll. It's the same server as what you're seeing right now, because this is a Jupyter hub. For Jupyter Lite, it uses fairly standard tunneling techniques. I can talk to them about you afterwards. All right, thank you, Balaji. He's our new service lead. He's been doing an awesome job getting everyone to actually use the things that we've built and don't tell everyone about. So happy to hand this off to him.
Thanks, Yuvi. Hi, everyone. I'm the service lead, as Yuvi said, for Data Hub. I work with Eric closely, and we work with instructors to use the data infrastructure during the instructional time. I'm going to quickly walk you through some of the other new use cases. I know we have only 8 minutes, so what I will do is just go through the slides and tell you what are the different use cases that we have updated in the recent times. And most of these use cases are for non-data 8 and data 100 classes. These are for more advanced classes which had different needs. And I also want to acknowledge Fernando Perez, who consistently pushed us for innovating these use cases, and Yuvi for architecting them technically. So the first one is Github Authentication. So the problem statement is that if I'm the instructor and I have students in my class who want to use GitHub as part of the class and push changes to the repository, how do I do that using Jupyter Hub? And how do I do that in a secure and safe way so that students don't lose their credentials? So that was a problem before. And one of the updates we made is we created a new GitHub app which allows for authenticating with your Jupyter Hub instance. And you can securely push changes to your specific GitHub repository. And this was piloted as part of Stat 159 course this semester, and it went really well. And I think Fernando will also talk about this in his upcoming slides. There's a short demo for the benefit of time. I'm skipping it. So the next new update we had is a sync thing. So the problem statement for here is that if I'm an instructor and I want to share my Jupyter notebooks and other files with my GSIs, and how do I do that within Jupyter Hub? Like, can I have a Dropbox-like functionality where I can put all my files within a specific folder and share that with the GSIs so that they can access it prior to the start of the semester? So we have this third-party application called SyncThing. We integrated with Jupyter Hub. And what happens is that once two different users within a Jupyter Hub handshakes by sharing their device ID, what happens is that particular file or folder that they want to share can be shared with the other user. and they can both access the same files and folders. And once again, this was piloted as part of STAT 159. This also we had good feedback, and we hope that multiple other instructors would use this in the upcoming time. And the third use case is the shared read-write. So this is the cool thing about this particular feature is that this is not present as part of Google Colab at this time. And what shared read-write means is that, say you are an instructor in a highly complex, has a highly complex data set. Say your data set runs up to 1 GB, and you want to share it with all your students. And you don't want 100 of your students downloading the same data set, storing the data in their drive, in the Jupyter Hub instance. What happens is that unnecessarily you are adding 100 GB of storage. So what you could do is that you could store your data set as part of the shared read-write drive. And what happens is that non-admin users, which essentially are students and non-GSIs, they can basically use their Jupyter notebooks and read the data from the data set. And as instructors or GSIs, you can store all the data, that data sets that you have within these directories. And we have been deploying this in STAT 159 course this semester. And we also have Biology Hub, which historically has a lot of genomics related use cases where the data sets are really complex. And they have been using it for the past 1 year, I would say. So as you can see here, like this is a shared read-write directory, and inside there is you can store your data sets as CSVs. The other use case I want to quickly talk about is the Linux desktop environment use case. What happens is that in certain classes, instructor wants to demo Linux-based applications or simulations as part of the class. How do you do that within Jupyter Hub instance? One of the solutions we came up with is setting up this Linux desktop environment. What happens is that you can deploy Linux UI-based applications like PyQt5 or QGIS, which is a popular geospatial application, or S9, which is an Astro application. So you could deploy these applications as part of Jupyter Hub instance, and you can showcase simulations that students can view as part of Jupyter Hub. This was used as part of EECS 16A. They had a UI-based interface they wanted the students to experience, and they used Linux desktop environment, and also STAT 159 used it. And I think one another instructor used Julia-based simulation as part of their class last semester. At least they tried to use. So as you can see, this is just a simulation that we created for Julia Hub. And students can basically explore the data using this. I think the other use case which I want to talk about is Serial Hub. The problem statement for Serial Hub is that, say, hey, I have a device which I want to which is connected to my laptop, and I want to read data from the device into my Jupyter notebook and also send data back. This was a use case that was presented to us by Electrical Engineering and Computer Science department. They had their labs, which was run pre-pandemic in actual classrooms, and they had to shift the labs to cloud infrastructure like Data Hub. They had to start using Data Hub during the pandemic. And the question was, how do we do that? And they innovated this. They created a Jupyter widget called Serial Hub. And the way it works is that the developer has created a set of code, and the students need to run the code in the Jupyter notebook, as you can see here, and they can handshake between the device that is connected to their computer and also the Jupyter notebook, which who knows, like maybe hosted in a server in Iowa. So this kind of a handshake setting helped the instructors to move their labs to Data Hub infrastructure, I would say. And once again, this particular widget is a work in progress. They are making a lot of updates to ensure that this is production ready. One of my favorite updates to the whole data science tool chain is the ND Git puller extensions. So UV created this Chrome and Firefox extension for generating these ND Git puller links that can be shared with instructors. Initially, you have to go to a specific page, you have to fill in the relevant details. And sometimes you may copy paste a wrong link. And while the ND Git puller link is pasted in the URL, you might get some kind of an error. But what this does is that once you install these extensions as part of your browser, it appears in the GitHub web interface. And what you need to do is just feed the URL of the hub that you are using, and also which interface, like is it Jupyter Lab or is it Retro Lab or is it Classic Notebook? You just note that, and you can copy a new link and paste that link in the browser. So this sort of simplifies the workflow, and we have been piloting it with multiple instructors this semester. Yeah.
I know, this is something that the instructor would do, and then they post the link for their students. And all that.
Exactly. The question is this, sorry?
Sorry, the students don't have to do it. They don't have to follow it.
Exactly. The question is this something the instructors have to do and not the students? Yes, the instructor needs to install this extension and they need to create the unique link and they just need to share it to the students through any medium that they generally use.
Thank you so much.
Sure. Couple of infrastructure updates. I think this is more non-application specific in the sense it's more backend stuff. I just wanted to highlight. The first is like, we have this class called Political Science 3, where the instructor is using a very unique pedagogy. Basically, he wants students to come to the class at the same time and log into their Jupyter notebooks and work on specific assignments. Sometimes what happens is that if so many students are accessing notebooks at the same time, it sort of creates like a resource constraint. Then the question is, how do we solve for that? So once again, we created a new extension, a calendar, Google Calendar extension, where we can schedule events saying, hey, between 3 p.m. to 7 p.m., we have this class and we want to provide additional resources to this class. And so when we add that, automatically the Kubernetes cluster, like our cloud infrastructure scales up and the students are able to access the notebooks at the same time. And this is something we have been piloting with multiple classes last semester and it went well, and we want to keep doing it with other classes. And the final updates is, I just want to show that right now, the way our repository, GitHub repository is set up, every time any change that we make to the base image, which has the packages like the Python packages or the R packages or applications, like we make changes to it. But we also have instructors make changes to the application and they trigger, whenever they push changes to the repository, they trigger the image build. For example, you can see in the left-hand side, Fernando, he itself made changes to the, he itself added packages and applications he needed and made the changes and pushed those changes to the repository. And he triggered the image build by himself. So this is something, just wanted to show that like we also have this sort of engagement with instructors. And finally, I just want to show some metrics. This is something we wanted to show yesterday's session, but we couldn't. Some of the high-level metrics. So this is typically how the Data Hub usage looks like during a semester. It starts off slow. Initially, we have around close to 1,000 to 2,000 users, but during the peak time, it's closer to 4,000 users. And at the end of the semester, as you can see, there are a few hundred users who use it. And if you look at the CPU usage, which is the amount of resources consumed, it follows the same pattern. Like initially at the start of the semester, it's very low. And then during the semester, during the peak assignments, it hits a threshold, and then it reduces at the end of the semester. And finally, yeah, the cloud cost. This is a question we generally get asked, so wanted to show how that looks like. So this is how the cloud cost distribution is. On an yearly basis, we spend closer to $100,000 on cloud cost, and depending on the assignments we use, the cloud cost goes up. As you can see at the middle of the semester, like during fall semester, there's a huge spike. So that's pretty much what I wanted to share. Thank you so much. Let me know if you have any questions.
Awesome. Thank you, Balaji. Thank you, everybody. We're gonna keep going if it's okay. You guys still with us? Yes? Okay, lots to take in. Make sure to go on the website for the conference and download the slide decks. There's so many links. There's so much stuff to try. There's so much, go find those slide decks full of links. Yeah.
That's not out yet. No, you get the
So
question.
the demo is in the slide deck.
Yeah, the demo has a link in the slide. Oh.
Yeah.
I'll add a link to the Jupyter Lite itself there. Okay.
No, but it goes to the book, and then within the book, look for the rocket. It's under the rocket. So what he did in the demo is he goes to that book, and it just looks like the book, but then you go to chapter 6 and look under the rocket, and there should be an option to Jupyter Lite under the rocket. So that's why he was really, it's like it doesn't take you right to the Jupyter Hub. It takes you and sort of like shows you. Yeah. Comments. Taylor Gibson, amazing work, UV. Any walkthroughs on how to implement RTC? So Taylor Gibson is a fan. Mahmoud is here, who works with Taylor. So they've done a lot of deploying stuff that you built at high school level in North Carolina. So it'd be a good person to work with just in terms of like, they'll build what's it like to deploy it in high schools. You can follow up with Mahmoud later. I'm going to switch. We are now entering another hour. Elias and I are going to talk about modules and connectors, and Fernando Perez is here to talk about his class, Stat 159, which has been teased heavily already today. Someday to be Data 159, hopefully. But I'm going to jump in. I'm going to introduce my colleague, Elias Saravia, who works with the student team that helps build data science modules for other people's classes. Thank you.
Hello, everyone. Yeah, so my colleague and I, Eric and I, we take part in data science curriculum development. So specifically, I work with the modules program, which introduces a lot of introductory data science material in classes that may not otherwise see data science applicable in their field. So I'll talk a little bit more about that. But just as a brief introduction, I have been working with the modules program and creating curriculum for over 3 years already. I love bringing data science into classrooms, and I'm excited to share with you all the different work that we have done. So the motivation behind all of this is that not a lot of students get to see this exposure of data science and what it looks like and how it's applied in their own field. If students wanted to see data science, they would have to take a data science course. But that's why we're here to bring data science to them. A lot of students tend to get a little intimidated by data science. So we want to make sure that it's accessible to them. And we want to make sure that it's also interactive. So that's why we use Jupyter and Data Hub, which I'll talk a little bit more about. We want to build bridges between faculty and students. And data science is inherently interdisciplinary. So we want to bring in people from sociology, people from environmental science to all work with us and show students how data science looks like there. So Jupyter Modules is bringing in a data set that is relevant to a course and introducing core data science concepts. Sometimes we're teaching hypothesis testing. Sometimes we're bringing in data literacy and showing data visualizations. But we aim to basically have all students, at least in Berkeley, touch a module and see what data science looks like in their field. So that's where we use Data Hub. Also, like Jupyter, that is a cloud-based technology to make sure that the computing is accessible to all classes. And we're motivated in developing the curriculum, and students actually come and take part in the curriculum development themselves. Sometimes they're going into the classrooms and teaching it. They're doing lab assisting. They're developing the curriculum firsthand. I also teach a course that helps students learn about pedagogy and how to create a lot of these notebooks. Oh. So what is modules curriculum? So yeah, they work on a hands-on data set relevant to their course. This could look like a lab assignment. This could look like a homework, a project, whatever it may be, a lecture as well. And they learn about the principles of data analysis, statistics, computing, all relevant to their own domain. And just to give a snapshot of some statistics, so we've been creating a lot of this curriculum for over 5 years, and we've impacted around at least 13,000 students have already seen modules in their own class. We've served over 80 courses. We've created over 250 notebooks, and we served over 40 departments. You can see to the right that our most popular collaboration with the department is the Environmental Science Policy and Management. And then right behind that is Biological Sciences. So I'll be sharing a little bit more about some examples of modules there.
Yeah, and we also partner with the American Cultures Department. So every student at Berkeley is required to take an American Cultures class. So what is an American Culture class? It shows a lot about the background of related to the American culture, and this can be seen through sociology, psychology, ethics studies, engineering. Every department has their own specific American cultures class, and all students are required to take it. We see around 100 to 300 students from all backgrounds that come into these courses. And we believe that collaborating with the American Cultures Department gives us also leeway to showcasing what data science looks like for them. And some students may not even decide to choose to learn about math, about data science. They're just surprised when they come into the classroom and see this data science introduction. And a lot of students who actually take some of these courses actually end up coming back to data science and say, hey, like I really enjoyed this experience. I want to help contribute also to this curriculum development. It's what's motivated me to learn about data science, and I want to see how I can contribute as well. So we'll go through some examples of some of where this can be applied. So we have worked with Ethnic Studies 21AC, which is a comparative study of racial and ethics group in the United States. It was with Victoria Robinson, and she continues to be a partner with us. And we worked on a notebook that talks about mass incarceration and prison realignment. And a lot of it is an introductory to data analysis. We talk about the data. We talk about where's the data coming from, who is represented in the data, who is not represented in the data, what is the data set, what does the row represent, what does the column represent, what does the data basically look like. And we also have something called widgets, where sometimes there's sliders, drop-down menus, or buttons that students can interact with data visualizations and compare different outputs. So you can see here that students get to choose an institution and look at what does the percent occupied of what does the percent occupancy look like in within a specific institution, and as well as looking at gender differences across prisons. In sociology, we have something called the neighborhood project. So students actually got to go into the field and collect data themselves. And then this data was aggregated for class-wide data. And they got to compare and contrast different values that they've inputted into the data, and seeing it geospatially, seeing it on a histogram, on a scatter plot. And they get to also use different widgets and select different parameters and variables and compare and contrast different things. So here they're looking at, for example, correlation and seeing how does a maybe bachelor's degree correlate with the median house value. Yeah, this is just also like an example of what the survey kind of looked like. And students could even click on the map itself and see who inputted that certain data point. And yeah. We also have one on environmental science policy and management. This looked specifically at geospatial data with the homeowners loan corporation, thank you, and tree canopy, and looking at how does redlining look like within Oakland specifically, and understand its social implications. Bio1B is actually one of our largest modules. So this has about 700 to 800 students. And this was a particularly interesting project because it happened during the pandemic, where students had to, they originally would go into a lab and collect field data. But because of the pandemic, they couldn't attend a laboratory. So that's where modules came in and allowed, we gave them the opportunity to create some of these simulations and create some of these experiments at home, and still be able to teach some of those concepts to them, but through a data analysis lens. And so we've done projects on bioindicators of a creek here at Berkeley called Strawberry Creek, simulate predator-prey interactions, and also look at evolution of mice over time. And students got to learn hypothesis testing and simulations. I don't know, do you want to talk a little bit about this one?
Yeah, I got to teach this cool field class this spring. And so I worked with the LIAS and we made up a data science module to go with the field class. There's some students that were doing study abroad at the field station in Moorea, French Polynesia. And they were looking at a tropical ecology question of like, what happens when you eradicate non-native rodent population? How does it change the ecology? So they had been doing field work and measuring things in the field. And then I was able to like bring a data set, and the Jupyter Hub worked across the Pacific Ocean. And so there was like able to bring like, I just want to say for this example, you can bring notebook-based learning into anything, right? These are like ecology students, you know, on a semester abroad, and they were able to do this really cool application that was totally relevant to the field work that they were doing. So just an example of like notebooks can be used for any sort of learning.
Yeah, it was a great collaboration. It was our first study abroad module that we were able to do. So we took advantage of that opportunity for sure. And then sometimes we dive into more technical courses like mechanical engineering, where this instructor wanted to teach fast Fourier transforms, look at air quality analysis. And he had a wind tunnel wave probe within his own laboratory, and wanted students to basically have data collected from that lab. And then students get to analyze based off of specific parameters and do some mathematical modeling and experimentation, and run some simulations as well. So the one in the middle you can see is a 2D simulating a 2D flow around a cylinder with vortex shedding.
So just to go back, like there's a couple of other important things. I'm just really passionate about notebook-based education and getting it out of CS and staff and data science and like across campus. That's sort of like one of my you know, passionate things that I work with Elias about. So the last class, you know, it was a pandemic and it was really hard to get people into the lab, to get everybody with a turn on the instrument to measure something. You know, all of a sudden you need a way that like 100 people in the class can get access to the experimentally collected data, do the analysis on it. And it's all ready, it's all there, you know, so they can record a video with like the GSI doing the data. And then all of the students in the class can use that experimentally collected data to do the analysis and do the lesson. And like, you know, there's the math behind it, there's the visualization of it, there's like bringing in the actual data that's collected from the instrument. There's like a whole bunch of those things that notebooks can bring together. And notebooks can bring, you know, sometimes we've also done biology ones where like basically the biology lab book will be like a Word document, that's the lab book. There'll be some way that you interface with the machine. There'll be something that you have to write up first in Excel and then put it, copy and paste that into Word. If we can do this all in a computational notebook, the whole thing, explaining the lab experiment, importing the data, analyzing the data, doing the lab book write-up, can all be in one rich document. So it's just a really cool inflection point, I think. And I think there's a lot of upside potentially in like different types of STEM classes that are outside of data science. A lot of students that don't want to learn programming, but there is this thing like, can we build bridges? This, you know, what Elias and I are exploring is like, can we build bridges to people who they can only, they're not in a data science class, but they're just going to need a few commands. Maybe there's a widget, maybe we've pre-done some data import and they just need to, you know, make a graph that's like the analysis. So what can we do to bridge out to those people and put the tools in other people's hands? Okay.
The students who develop these modules, do they do that voluntarily, or is there any support for them?
Yeah, so sometimes students do it voluntarily. Sometimes we also have paid positions available. And yeah, students are just come in with that passion saying like, I also want to learn what data science looks like in other departments that are not what I've worked on previously. And so I want to help contribute through that curriculum development. I have that passion for education. And so they come and work with us for that.
It's also some part of portfolio building and a project-based work. So some of the students that are really amazing, like they'll graduate and they'll come out of this program and they'll have a bunch of project-based work that they've done for, you know, a social justice class. Like they're interested, you know, one of the students that did the module on, you know, the prison mass incarceration, you know, motivating like the social justice students to study data science. Like she's gone on to her PhD in education. She's totally into like how to make, you know, socially engaged research part of education. Like that's her topic. So when she was applying the PhD program, she had this like, portfolio of work that she had done and contributed to. She also had time in the classroom. So sometimes the data science students come into the classroom because the peer-to-peer learning of the data science students to the other types of students is really strong. So there's a whole bunch of different ways that people paid, unpaid, credit hours, different modalities.
To implement this module, the student need to download the Jupyter notebook and all the software that they can data, or like web links and they don't download it.
It's actually very simple. Like they really just get an interact link where students just click, and then they're directly sent to the UC Berkeley Data Hub, where all they need to do is sign in with their UC Berkeley ID, and then they have access to that directly. So they don't need to download any sort of software. They can just go straight to the web page. Yeah.
Okay, I'm gonna do connector courses just for a few minutes, another big passion project of mine. And as these things go, this is what I do with another part of my time. Half of my time, I am a staff person for Berkeley Data Science. Another half of my time, I am a lecturer for Berkeley Data Science. So connector courses, John already motivated, so I can skip over this. They're 2-unit classes. You're in Data 8, you're learning fundamentals of Data 8, and then you're learning something else that's applied. So we have a whole set of these on earthquakes, on neuroscience, on genetics, economics. We'll get to that one. The one we had this year was data feminism and global studies, like a new instructor. So we're building notebooks to sort of bridge the Data 8 methodology to some sort of topic and giving the students some sort of application. This also comes up in program planning and a lot of universities that are trying to build, like, how do I engage the faculty outside of CS and stats in this project of data science? So this was sort of also, if we're going to go meta, like part of like building the program and getting stakeholders involved from departments across campus and what this data science initiative would be. So my class that I've taught for 6 semesters, sorry, I have to talk about my class, similar, but I want to say, like, as an instructor, similar to Data 8. So you have the interactive textbook. I have a student team that sort of helps me build the notebooks and helps me teach it some of the times. Everything's published in there. If you know anybody in econ who's interested, they can go like look and download all the materials, or they're all out there. So my idea is connecting data science with economics. So data science and economics have an interesting history. Like when I was getting my PhD in economics, we did a lot of regression analysis, and we became some of the early data scientists. Like the people that were graduating in my field were what data scientists were beforehand, because they had a lot of experience with before machine learning. It was like regression analysis was the thing. So I'm sort of trying to motivate econometrics. What's happening with data before you get to econometrics. But we bring in people, we bring in guest speakers, we bring in people working in quantitative fields, and we give students exposure to some fields. If they want to go into econ, they're going to want more tools. So LaTeX is a thing. Supposedly, suppose you want to go ahead and go to a PhD, you're going to want to know LaTeX. Nobody ever teaches you LaTeX. So where is that missing? And sort of like looking at economics literature and understanding questions in economics literature. So it's a whole set of Jupyter notebooks that are based on, economics concepts, widgets, LaTeX, symbolic Python, econometrics. You just briefly touch on all sorts of things. There's a huge population and a huge interest. So like I built this with some students, and Chris Piles, who was here, and some other students. We built it, and every semester there's 100 students that sign up for it, and there is a double major, it's one of the second or third biggest double major in the data science major. So there's something like 150 double majors between econ and data science. So I'm like trying to teach into the space that the students are already in and they're already interested in. It keeps growing, keeps evolving. Here's some examples. These are all things that you would see in a classic Econ 1, Econ 100 class. That your midterm in Econ 100, you would draw these with a pen and paper. And so one of my goals for the class is like, you should be able to draw the things that you're, motivating: Cobb-Douglas production function, consumer surplus, average total cost. These are all like Econ 100 concepts, and you're building them so that the students can interact with them with Jupyter, with Python commands, matplotlib. So it's like the students are basically getting more skills on programming Python, but like by applying it to things that they know from their Econ 100 textbook. So Also, I'm trying to motivate this idea of like this, I think is the future of textbooks, interactive textbooks that you're going in between and you're gonna get a sample of code. You're gonna like, oh, I know how to do that in the textbook, but the code for me to implement that can come from the textbook. And I think that that's sort of like a disruptive moment that we're at in education with changing what textbooks are. The way I got into this, when I was at a course like you guys, like a Data 8 boot camp, they used to offer for instructors. I had been a postdoc working on a Gates Foundation study in Africa, promoting water garden, measuring that. So this is how I got into it, and sort of early ideas about reproducibility. So what would it be like to publish a journal article where you publish the code that generates the graphs? So that was my original vision for our class, was I was like, hey, this is what data looks like when it comes from the field that somebody's gathered on a clipboard. What does it look like when it goes to the journal article? And what are those steps? What is those dirty, messy steps that data takes between field collected data and data that's submitted for publication? And that was my original intro. Somebody asked about the business school. So there's the business school class. Just as an example, an instructor, he got it. He was like a data scientist and a coder. He's worked at Airbnb. He made a whole set of lessons. So this is like a core class. If you're in the business school, you take this class and you learn a whole bunch of skills. This is taught, over 100 students a semester, every semester, forever now. So this is like a thing where like people are coming up through this with this new set of tools. And so undergrad business, really big major, really well motivated to have the students have a nice skill set by using this connector application. This was an amazing one that was around for a while. It's not taught anymore, but they gave students access to fMRI scans. So this was the kind of thing where the Jupyter Notebook made what was basically like PhD level research available to undergrads, right? So some really amazing PhD and postdoc were able to make this amazing set of notebooks with real world fMRI data. And you're basically like taking something that's like super complicated and making the tools available to people early on in their education. So, these kids can go on and be, part of a research team. They can be in somebody's lab. Lots of info. If you're interested, there's, as Elias said, there's hundreds of notebooks in dozens of different fields. So if you're interested, come browse our repo or ask us. We're always looking for ways to apply things. We're always looking for collaborations. We're always looking for interesting applications. Okay, I'm gonna wrap up so I can hand it over to Fernando Perez. Any quick questions on?
Do you have any connector courses to arts departments?
Yes, we definitely have. There's been an English one, there's been a philosophy one, there's been an arts one. There's an amazing guy.
We had a module, music.
Yeah, there's a music one. That was cool. Yeah, so you just go find. It's like we're like, how do you find your champions? How do you find your related people? Yeah, Greg Niemeyer in the art department. And then I can't remember the name of the guy in there's a Center for New Music off campus. So he had already done like experimental music with Python. So he was like ready to go there. But then we had the students that we work with that were like musician students, and they were super psyched. And they're like, oh, please, can I be on the music one? I'm really excited about, what is it like to make music with a Jupyter Notebook. So yeah.
I haven't followed up in a while, but there's a very cool project out of MIT called Music 21, which is a set of libraries for like, I think it's more a little bit more on the musicology end of things.
Yeah.
And it does have notebook support and has a lot of different support. So maybe.
So we built some using Music 21 for this guy, and I don't know how many times it's been taught, but I know that we've built some of the notebooks for him. Without further ado, the absolute legendary Fernando Perez, without which we wouldn't be here talking for days and days about Jupyter Notebooks.
Goodness gracious. Well, it's great to be here. And the previous two talks have been a great segue for what we're going to talk about. So I don't think I have to frame things too much. For those of you that I haven't met yet, I'm Fernando. I'm faculty at the stats department, part of this data science effort. I actually came to Berkeley originally to do fMRI. My first job here at Berkeley was a scientist developing a tool for fMRI. So probably know some of those people. I'd like to know why the course hasn't been taught.
I know.
We connect with that group. But
And
anyway.
somehow he does like environmental data science, astronomy,
neuroimaging, all of them happen. But anyway, I do want to talk a little bit about kind of visual research, exactly what Eric was talking about. I think how we do science is changing. I think we're at a really important moment of change in science. The last 20 years were, I would say, the rise of what I would call open source in science. And now
Could you stand here because
sure.
of these two?
And to some extent, I think we sort of won that particular kind of debate in that science is now being done with open source tools everywhere. I'm not going to rehash that, but I think the cloud is opening new doors, and we wouldn't be here having these conversations if it weren't actually for cloud infrastructure. I highly recommend that you take a look at this particular paper that came out, published among others by Yubi, who's here, who was one of the co-authors of this paper, as well as Chris Holgraf, also from Berkeley, led by Shel Gentleman, an oceanographer from the Bay Area right now at NASA, about kind of the change that the cloud is introducing to the practice of science. For example, both Shel and Julius Buseke, two oceanographers, Julius is in New York, kind of posting how they're doing effectively research cutting edge level science, either on their phone in the subway or off a $30 Raspberry Pi at home, by leveraging the cloud to analyze terabytes or petabytes of data. Shel is leading this at NASA. Quick check. Who had heard of this in the room? Just one person. So a couple of people, 2 or 3. I would encourage you to take a look at this initiative. It's amazing. So NASA has now published as official federal policy known as SPD 41. This is Science Policy Directive 41. This is federal policy now, that all NASA science from now on is done under an open science model. But I don't mean that's if you can figure out where the postdoc who's now hiking in Indonesia left the hard drive, there's a way to get the code. No. We're talking projects will be developed under an open source model with openly available repositories, with community governance, blah, 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 blah. I mean, they've really done their homework. Shel Gentleman has done a lot of the leadership behind this. There's a deep commitment to diversity. There's a deep commitment to democratizing science. And they're developing materials, technical stuff, educational workshops. They're working with AGU, the European Space Agency, and the Japanese Space Agency, as well as other federal agencies, USGS, NOAA, NSF, to really push the model of open science as the way in which to work. And I think the cloud brings some interesting elements to the conversation. We have open data. It's not perfect, it's very complicated, but there is a lot of openly available data today that can be put next to scalable computational resources that we can deploy next to the data. The data is too big to move. The compute now is the thing that's small and lightweight and can be moved around. And we can embody that computation with modular tools that we have the right to assemble, recompose, and deploy in the ways that we need. That's exactly what you've been seeing this morning. And with these 3 elements, what we have is the possibility of tackling problems that go really well beyond sort of traditional disciplinary silos that require societal engagement in new ways. I use the analogy of the digital watering hole because I think of the watering hole as a place where both the lions and the zebras need to come together, and not because they have a common need, the water. And our water is our common resource is a combination of data and open computation. And I think this will give us the possibility. I'm not saying it's a panacea. Tech is never the panacea, but at least it gives us tools to tackle scientific challenges that go from fundamental research to education to societal engagement and decision-making. And I want to use an example as an example of this kind of mental model and workflow. This class that Eric already mentioned, Stat 159, which is called Collaborative and Reproducible Data Science. It's a course that is very much inspired by this quote that I've used many times in my talks. Originally from David Donahoe, was paraphrasing David Donahoe's in stats at Stanford, and he was paraphrasing John Claerbout, a geophysicist who had, back in the 90s, a model of reproducible research, not out of the goodness of his heart, but rather out of being productive. He basically said, I don't want my grad students to spend the first 3 years of their PhDs redoing what the previous grad student did, and then only having a year or 2 at the very end to do something new. I want them to hit the ground running, be able to replicate what had been done before by typing make, seeing that everything works, spending a few weeks understanding how that worked, and then doing something new for 4.5 years, not for a year or 2. And David phrased this, David and John Buckheit, they phrased this in 1995 by basically saying that a paper is just advertisement. The PDF that you download of a scientific publication, it's just an ad. It's the glossy brochure that's an ad. The thing that's the real work is the code, the data, the details. And today we would probably argue the place where you can run all that, because it's not trivial to put it together, right? To actually convey what were those ideas in a usable fashion for others to build upon, right? And so Stat 159 is a course that, inspired by that, tries to teach our students, first of all, what? Some fundamental ideas about the role of data, computation, and statistical analysis in the workflow of science. The why that is important. So there's some thinking kind of about somewhere at the intersection of ethics, technical ideas, and epistemology around why open science, why research ought to be reproducible, what are the kinds of ideas that we express in code, including, as I said, ethical and epistemological questions. And then obviously a lot of work on the how, on building the skills, and I want to emphasize the habits necessary to make open reproducible science a viable construct, because it is about habits. It's not about at publication time when my paper gets accepted, then I promise, I'll clean it up, I'll document it, and I'll test it, I'll make it reproducible. No, by that point, really, the horse has left the barn. So this is a course where we try to teach all that in the context of roughly 2 lectures. Last time I actually taught it in one long lecture. We have basically a lecture component, a lab component. The course was started by Philip Stark, my colleague in the department. We've had, over the years we've taught it, we've had 3 fantastic GSIs, and they've done really a lot of the work to make this possible. It's cross-listed between undergrads and a few grad students, and they do a few different things, but by and large, the course is really the same skills for all of them. We have a combination of reading materials, homework, and projects. All of this can be, you can access the various editions are obviously all open up on GitHub. These are some generic stats just to give you a sense from a couple of editions I haven't updated with this year's, but to give you a sense that the mix of majors who take this course, even though it's listed as a statistics course, is pretty broad. Well, majors in undergrad and also PhD students. This has led to me being on the undergraduate thesis committee and quals PhD committees for a bunch of these students. So it has actually brought many students to say, I want to do my PhD, I want to do my master's, incorporating some of these ideas. Can you be on my committee? And kind of pushing this across departments. So I've managed to now be in nuclear engineering PhD quals committees and astronomy and geophysics and a bunch of that. On the idea side, we try to talk about basically every week. There's something that they have to read. Either we have a reading list that includes papers and blog posts and some videos, where we kind of try to tackle a little bit more of the high-level questions, including, as I mentioned, questions about challenges with reproducibility, epistemological questions on statistics, and really the foundations of scientific trust and validity, the community incentives. And there's a little bit of an active discussion led by the students around that based on what they write. And then on the how part of the course, it's really about concepts embodied in practical skills. So the course specifically is based on learning how to do these things, but each of those things embodies an idea, which is generic. You can teach a version of this course replacing the tools by whatever you want, right? You could say, I want to do this with Julia, and I want to use GitLab, and I want to use whatever the tool of choice for Julia for each of these tasks. It doesn't matter. What is important, I believe, are the things on the left, that each of these ideas is an important skill which is not being taught. I also teach a course like Data 100, which is the operative successor to Data 8. They learn a lot in Data 100. They don't learn any of this. I mean, they learn a little bit of programming, but not even that. We really don't talk about programming. We don't talk about testing. We don't talk about the expression of programmatic and algorithmic ideas all that much, because the emphasis of that course is in other aspects. And we are seeing a huge demand from students of all disciplines and desperate demand from the grad students on, can we learn more about how to do computational science in a robust, sound, and reproducible way? And so, as I mentioned, we try to do this by instilling habits into them. By habits, I mean, it's a lot better to brush your teeth than to get a root canal, right? It's less painful to brush your teeth than to get a root canal. And Git is the toothbrush science. And so they learn to brush their teeth, and they learn how to use the toothbrush on day 1. And we only talk about the toothbrush for a day, because after that, they have to brush their teeth every day. The class is run on Git. The class is run on GitHub Classroom. The class operates on this infrastructure. So they have no choice but learning. Now, we teach them concepts, right? We can have a whole conversation about how I teach Git, Git is a tool that is maligned because it is taught poorly, because it is taught as a randomly assembled collection of inscrutable and incomprehensible commands that spit out arcane error messages when you type something wrong. And there's no mental model behind it. Whereas if you teach what the actual mental model is, it works fairly smoothly and anyone can understand it. Anyone who can draw bubbles and arrows on a board can understand what it does and why it does what it does. And when they understand the what and the why, then they can piece together why the error messages have come up. But then when they have that concept, they have that foundation and they operate on GitHub Classroom for everything. Every homework assignment, everything they do goes through Git, which has the side advantage that the dog cannot eat their homework because GitHub is too big for their dog. So the dog cannot eat all of GitHub. And this has already saved a bunch of students from trouble when things go wrong, that they have all of their infrastructure up on GitHub. GitHub Classroom, for those of you who haven't used it, is a little add-on to GitHub that basically semi-automates a few of the common things related to things like, I want this repository to be the basis for a homework assignment, and I want all the students to have it, and I want it to be based on a private repository that only these students have access to, and it's a group assignment, and I want it to be this deadline, and so on and so forth. It's not a huge deal, but it does automate a few things that are common in kind of classroom settings, so we use it. Not a big deal. And students turn in their work in the form of GitHub repository, right? That is the object that they turn in, which means they're also learning a skill that is going to be very valuable, whether they do academic research in the long run or not. They're becoming fully conversant in this, and not only as individuals, important, but as teams, right? The title of the class is collaborative data science, so it's also working as teams. They learn how to build repositories that contain things like make files and environment descriptions, so on and so forth, that we're going to talk about. They live this kind of reproducible life for everything. And so because they're living in a hub, they learn, how do I manage my configuration of my environment so that when I move from one hub to the next, everything feels the same? How do I structure my home directory? How do I manage my computational life? Because we're going to get into this notion that as much as I love what Eric was saying about learning around notebooks, it's more than notebooks. And we're going to talk about that in a second. So in here, we talk about, well, okay, that code that those notebooks have that you are running to visualize your data, what does it need to run? Right? What else does that code, what libraries are you using? Does it make a difference whether you're running version 1.2.3 or version 3.4.5 of that library? So they learn about the concept of dependencies. Very basic concept in software engineering, really important to do it right. The point is that they learn how to manage that, not by scribbling it on a Post-it note, but by writing that information down in a machine-readable way so that machines can read it. If a computer can replicate what you did in an automated way, another person will be able to do it too. Because they will be able to pick that up, pick that computer up and use that to replicate your work. So they learn about things like Conda environment management and the kind of technology that is used to manage dependencies. We've already talked about these book collections. So they learn how to build Jupyter book websites, right? How to go from, I have a collection of notebooks and Markdown files and maybe restructured text files, for those of you who know what that is, if not, it's just another text format. And I want that collection of documents to look to the user, to the reader, like a decently formatted and structured website. How do I go about that? And how do I publish that? Well, Jupyter Book is a tool that assists in that. This is an example of the Data 8 textbook, and they learn how to do that. Now, if I have this collection and it's visible to someone, how do I get them not just to be able to read it, but to run it, right? And this is before Jupyter Lite exists. And Jupyter Lite opens other possibilities, and it's very, very attractive. But we've had for a number of years another project that began actually out of another neuroscientist. In this case, Jeremy Freeman was at Howard Hughes Medical Institute when he started Binder. Binder is a project that is now developed kind of by the Jupyter community, folks including UV and others. And the purpose of Binder is precisely to say, you have this collection of materials. Okay, somebody could view it as a website. How do they run it? You would want to give them a way to run it without having to download and install and read all these instructions and then click on this and this and that. What if you could give them one link they could click on, and that's it? They open a browser and everything works. That's what Binder does. Basically, behind the scenes, what Binder does is it takes a collection of Jupyter material. There could be other sources as well, but for the sake of simplicity, let's say a collection of notebooks that are stored on GitHub or similar. that importantly have those dependencies listed. The machine has to be able to know what does this need in order to run. You have to say that, right? If you don't say that, there's no way to guess that, not reliably. So if you said that, then the system takes care of some cloud-related buzzwords that don't matter for our purposes and shouldn't matter because you don't need, the point is that you don't need to be an expert in Docker and Kubernetes and all that. You simply, if you have your content and it is under version control, and you took just a minute to say, my code needs A, B, and C to run versions 1, 2, and 3, you're done. If you brush your teeth, you don't get a root canal. You get a link that works, and you share that link with the world. They click on that, and they open a web browser, and it just runs. And the name binder goes back to that quote from David Donahoe, right? The PDF is the brochure. It's the sales pitch from the real estate agent that has like the glossy one pager for the house you want to buy. That's not what you want to buy when you buy it. What you want to see when you buy a house. You want to see the 3-ring binder from the inspector that has like, what's the state of the sewer lateral, right? And what are the toilets like? And how much am I going to have to spend rewiring the house, right? That is what you need to know. What's under the hood? It's the binder that contains all of the background materials behind that glossy brochure. And that's what binders gives you. Now, all of this, once we make it automated and automatable by the machines, then machines can do work for us. So for example, the course itself is structured around GitHub Actions. GitHub Actions is a service, just like the Circle CI service they described earlier, that GitHub provides for free, where any repository that you have, you can specify, when new code arrives on this repository, I want this to happen. You get to say what this is. You say, when new thing arrives, I want the following code to run. So for example, when there's a new commit to the class website, automatically the website gets rebuilt. We specify how this is done by having a specific file in a location called GitHub Workflows. And this file defines a name and a set of actions to execute. That name says deploy book. When any new work goes in, deploy book is executed. GitHub shows us what happened, how long it took, in this case, 37 seconds. And then we get a log of the details. And in this particular case, the website is built. This idea of having GitHub itself automate is one of the benefits of doing things in a reproducible, machine-readable, automatable fashion, right? We say we want these things to happen. GitHub does the work for us, right? And the students benefit from this because I commit to the repository 1 minute before lecture in my office. I walk down the building, I show up, and they see the website is live because the commit happened 35 seconds ago, and it has been built and deployed on the internet. And that same workflow works for me. As Balaji was showing earlier, the infrastructure repository with where all these hubs are deployed, right, is actually a long list of descriptions of systems like this, in this case, for running the class, right? And I get, as he was showing, I get to make those changes, right, myself, and with the same exact workflow that the students are benefiting from for their content, right, we run the class itself, and we run the entire campus infrastructure, and there's a huge benefit to that. Now, the class, I figured, had to be imbued with something that mattered to the students, and we have in Data 8 and Data 100, minus the connectors and the main courses, we tend to focus on tabular data sets, and there's a lot of reasons why that's good and valid, but not all data in the world is tabular. I'm a physicist by training. My original training is in physics, and data is not always tabular. Spatiotemporal data tends to come in other structures. I want our students to learn about other tools. Data that comes from physical models not only is managed with tools like dense and dimensional arrays, it also has physical models behind it. So doing data science on data from the physical world is not only about doing ad hoc feature engineering and model selection, it's also about thinking about the connection between the physical reality of the models and the implications in the data that they're seeing. And finally, there's more to the world than building tech for industry. Now, many of our students will end up building tech for industry, and that's great, and that's fine, and those are perfectly legitimate professional paths. But we also want our students to think, are the skills they are learning valuable and important for things like the climate crisis? And so what we did was we used climate data, and we had a wonderful guest lecture by the same Shao Gentleman from NASA, where she presented not only some classic, like the Mauna Loa CO2 data set to introduce the students to basic time series data, spatial data from looking at ERA5, which is one of the big climate reanalysis data sets that has many climate variables accessible in one place, to kind of learn about this combination of new tools, new ways of thinking about models, and the application of this data to a problem as important as understanding the Earth. Then they had to do a project that was based on her research. The last paper she wrote, which was looking at the heat waves we had in California in 2016, the last paper that Shell wrote before she kind of became a convert to open science and Python, which was done by hand with a bunch of MATLAB scripts that took her months to process this data, and where she put a little footnote at the end of the paper, code available upon request. Classic thing, she meant well. And so what I tell them is, okay, you have an opportunity to play that game. You email the author, they don't have to email the author, they get a repo on Github Classroom that has those scripts. It's as if they had emailed the author and they got a zip file that says, yeah, here are my scripts, good luck to you. They have the paper, they have the scripts, and they have a little starter notebook that says, here's the data, because we did save them the pain of manually downloading all the data. It took Shell months of work when she did the original process. And then the challenge they have, these are not climate science students. These are a random collection of Berkeley undergrad and grad students from all disciplines, and they get to work about this data that many of them may have experienced those heat waves if they were here a few years ago, and work on replicating these figures from this paper by working with the data directly. So they're doing actual reproducibility of real world science from a paper that was published at AGU a few years ago. After that, the students get to do a real world analysis project, where basically what we've done is we've created kind of a standard playbook. We say, the way in which you present these ideas back to Eric's experience in Africa should be offer a standard package that includes the data available either in the repo if it fits, if it's small enough, or a link to it if it's open elsewhere. Code that is tested and documented and clean. Analysis notebooks that have all the gory and gorpy, messy details of wrangling the data and making the plots, and they're typically nasty and messy and finicky, because that's the reality of making real world research and real world analysis, right? But the scientific story that you want to tell, the paper, if you will, is a narrative notebook that shouldn't be full with code. It should be picking up the figures, the tables, the code, etc., done in the others, summarizing it into a thread of a history, of a story that is the story you are trying to tell, the question you're trying to answer from the data set, and then that is supported by the right practices, licensing, environment management, etc. And here's just two examples that I took from what the students did. These are two screenshots of two Jupyter books that they turned in, one on air quality in the Bay Area, for those of you who were not here a couple of years ago. These are photos. This is not some CGI, right? You may have seen this in the news. This is what our windows, the view outside of our windows looked like a couple of years ago when we had those really horrible wildfires that sent smoke into the Bay Area. And another team did a study of a breast cancer data set, just to show you a little bit of like the thematic diversity of what they worked on. There were obviously many more. And as an example, the Jupyter book that they provide has a main document, which is this document that has a section on data exploration, a section on high-level visualization, their analysis, conclusions, author contributions. Now, they have to write an author contribution statement like in a scientific paper. We have the Git logs to check on that, right? They have to work on Git. We ask them to review each other's code, to discuss on GitHub, to work like a scientific team, right? And we see all that. And so we have the story behind all of this. Now, this is the main story. How was that accomplished? Well, if you look at these figures, the code, obviously you can read, but you can see that it's a teeny amount of code before any figure. That's because the main narrative should only be presenting the figures, the results. It's telling you a scientific story that you can read. Then you go into the analysis notebooks that are multiple notebooks that are gorpy and have a lot of detailed code that produce each of those figures, that visualize, that animate all of that data so that you can see all of that. And then how did that get done? It was done by code also. And the code is available in a library that is installable, that has a properly documented API and properly documented function calls, that has tests that go along with it. So this is a supporting infrastructure for the work that they're doing. And the entire thing is delivered as a proper GitHub repository that has a binder link. And if you click on the binder link, it takes you to the live version of all of that hosted in a hub that you can run and you can play with their research projects without any further work. In addition, obviously, to having the JupyterBook version that I just took the screenshots of. So the students learn to go from zero, right? They have had data 8, data 100, they have had the other basics. But they go from zero on this kind of workflow to turning this in by the end of a semester as basically real research level. Well, I mean, we don't ask them to write this in a way that would be published as a scientific paper in the literature, but at least it has the structure of an original analysis where they did their own explorations. And they do this by getting an experience of real computing. It's not just about notebooks, because what they have is either they're running on this hosted installation on one of the hubs we talked about, it gives them this kind of environment with Jupyter Lab, not just notebooks, or they're running on their laptops. And they do learn to get both, because we teach them how to install everything on their laptops halfway through the semester, not at the beginning. But then what they get on the hub is not just notebooks, and this is important. They learn to work at the terminal. They have file management. They have text editors that can edit LaTeX files, Markdown files, Python scripts, right, that can render a Markdown file as they're working on it, because there's a tool in the Jupyter universe called Jupyter Lab, which is basically our current interface. And it really is a complete development environment for data science and for exploratory computing that has access to viewing data sets. So a CSV viewer, there's image viewers, there's tools to work with other kinds of data like diagrams, for example. And in addition to that, the system actually offers, for example, a launcher into a virtual desktop, because we may need tools that only run on the desktop, tools that are not part of Jupyter. So there's actually a virtual graphical desktop that the team set up that allows us to say, if we need a tool that isn't easily exposed in Jupyter Lab, right, then they can view it through a graphical desktop. We have a tool called SyncThing that they configure that is a Dropbox-like tool to share data between, say, the hub and your laptop, so that you can just like download files on the laptop and they just show up on the hub. Nothing else to do, they just show up right on a folder. It's kind of like magic. It's like having Dropbox for a specific folder between the two machines. And what this lets me do when you kind of adopt that workflow is live my scientific life with hardware, in a sense, being basically a collection of keyboards and screens, some of which are small and portable, some of which are big and comfortable, and they sit on my desk. But my work happens wherever I either need a specific technical tool or a specific team. So I have a hub for research for my group managed, and it lives on Amazon, on AWS, for various reasons. It lives on AWS. Our campus hub, which is the one that I want to go to when I want to see my students, is the one that we were discussing that the team has set up, lives on Google Cloud. My laptop is the machine that I can use when I'm on an airplane without Wi-Fi. When I'm working with my colleagues from LBNL, I need to work on a supercomputer up the hill called Perlmutter. It has a Jupyter Hub that runs on Perlmutter. When I'm working with a new team of heliophysicists at a workshop in Colorado, we stand up a new hub in the cloud for that particular community. For me, all of these environments basically are just, think of it like opening Dropbox on your phone, on your iPad, on your tablet, on your laptop, but it's all of your work and you don't really care where it is. What I care about is either specific hardware resources or specific teams and communities that bring me to one of these, but I have a unified view of the computational experience across these. And all of this is possible because of the work that they have done, right? When I have a problem with this repository or I have a question, I hop on Slack. These folks immediately hop on and we have a discussion. And it's not only people like Yuri, who is here, and Balaji, who is here, or Ryan Lovett. I don't know if Ryan is here in the room, or John Felder is here. Yeah. Okay, great to see you, John. And many others from their team who have made this possible. One point that I want to flag is that if you look at who has contributed to this repository that has all of these things, as they mentioned already, as Balaji already mentioned, there are people there like myself. I recognize Josh Bloom. I recognize Andrew Bray from the stats department. There may be others there. Those are instructors, right? This gives us a place where we can actually work together. This is not about me asking for something and they doing something. We can work together, and it's a much better way to work. We work together in this way. We do the builds, we do the commits, we add the things that we need. They ensure that it's done correctly. They help us if there's some detail that we don't know, but it's a far more participatory and constructive way to work. And I absolutely love it, and I hope it's useful to some of you, and thank you for your attention.
Few questions? A lot to take in.
You said we could ask people about how you teach Git. You have, I'm assuming that's a very long conversation. Do you have resources you can share or?
Yes. Oh. Let's see. Real quick. Let's go here. This is the class site. And so I have on the class site, which is linked in the slides, we have this little notebook. I still need to finish cleaning it up, but it kind of needs to go along with my own narrative, but it has the pieces. That's the one that I use, and you may find useful this particular. I need to fix something in the rendering of this one. I've already fixed it. I just need to push an update, but there's a link there to this particular slideshow that I have in there. So I'm accessing this from like this notebook that is open, so which means you can follow the same trail of links, which is this little one where I present Git as a tale of bubbles, arrows, post-its, and stickers. Those are the concepts that matter in Git. And I basically try, I'm not gonna get tutorial in 10 seconds here, but I basically try to work through this little sequence of diagrams that identifies very specific concepts in Git, like commit, what commits are, what hashes are, what head is, the differences between branches and tags, connected to the actual Git commands that you would issue, but presents this. Git is not a version control system. Git is a tool for doing surgery on DAGs. It's a system for manipulating graphs. And that can be illustrated visually very easily. It can be connected to the commands, and the companion notebook, which, as I said, I do need to fix one thing in it so that the image is rendered correctly, also has the actual Git commands in Bash and the log output that shows that those bubbles and arrows that I drew visually actually correspond to the real output that Git generates at the command line. So I'm not faking it, right? I am trying to clarify what the right abstractions and mental model are, but I'm not faking it because those do correspond. And so what I call A0 is a shorthand for a hash. And that specific time that I run that becomes hash CAV4558. It doesn't matter. I call them A0, B1, B3, B4, because I wanted to have short things that I could put on the rules slide. But they are real. The topology of this graph is the topology of the diagram, right? That diagram gets built by these commands, and the number of individual concepts that exist in that is really just these. These are the concepts that matter. And the other thing is that we start in this tutorial by implementing Git. This is Git. It's 9 lines of Python. Git can be implemented in 9 lines. The core idea that matters can be implemented, and the students can see it in action. Once they see that in action and they understand the mental model, then all the gibberish from Stack Overflow can make sense. If you try to make sense of the gibberish from Stack Overflow without a mental model, it's an impossible task. So that's why I do prefer to approach it this way, and I hope it's useful.
Thank you.
It is very opinionated. I'm sorry, I have a really opinionated take on this, but I think I have the evidence to back it up. Please.
The data wrangling and exploratory space have a lot of restrictions and freedoms and choices that might go on, the back end of a lot of local, but usually don't out in the context. What tips for presenting and summarizing what those points were, so that later here understanding of these different important tasks?
God, the one thing I do have them do is read Delman's paper on the Gardner forking paths, right? So we do try to discuss some of those points a little bit, but there's a lot of work yet to do in this course, and I don't know that I can do justice to this. I mean, that question is so deep and so important that I don't think I can do justice to it right now. What a student gave me an idea for, at the end of this course was actually he prompted me by asking whether I had a second semester version of this course. And as we got talking, I realized that I do have enough things pending or half explored that I think I need to develop a second version. This summer with my grad student, I'm finishing basically, this spring edition was the first time that I felt like, all right, this is okay. It's still like the actual courses on the website are a mess. But now, what we kind of have in our heads, now we know what to do. So I think we're going to try to clean up what we have for the next spring where I'm going to clean it. And I think it'll be like reasonably ready. And then I hope to develop a second semester edition of this course that I think would really benefit, especially graduate students. And then I think that's where I want to dive a little bit deeper into topics like that. Also, for example, the topic of how do you test data analysis, not software, data analysis. That's a nasty, fascinating, but nasty open-ended question where I don't even have the right answer yet. But I would want to explore them in a second edition.
If you could incorporate this like the bias and pitfalls in there as well.
So those are great suggestions for when we develop basically the B, what we call the B part of that, of hopefully this course, if I can get it through, we can get it to campus, and maybe some of the wonderful
There you
folks on
go.
the team can help us.
Yeah. Okay, thank you to Fernando. On the schedule for today, I forgot to put the time for the coffee break, so you're here for 2 more hours. Just kidding. There's coffee and cookies over there, so take 15 minutes and stand up and walk around and get sugar and caffeine and come on back. Hi.
If you want to go get coffee, I completely understand that. I just wanted to ask you a question about data 8.
Yeah.
If I may. Because there's so much new